Hello everyone, welcome to Neso Academy. We are learning theory of computation and till now we have understood what is a deterministic finite automata and what is a non-deterministic finite automata. I have explained you that in case of DFA, for every current state, there is only one next state possible for a given input symbol. But in case of NFA, for every current state, it is not necessary that we have only one next state. There can be multiple next states possible, which is a non-deterministic behavior. In practical implementations, it is required to remove this non-deterministic behavior from an NFA. And in order to remove this non-determinism from an NFA, it is required to convert an NFA into its equivalent DFA. So in this lecture, that is NFA to DFA conversion introduction, we are going to start with one of the most important topics of TOC. That is the conversion of non-deterministic finite automata into its equivalent deterministic finite automata. In your semester examination, you will surely get at least one question from this topic. So in this lecture, we are going to convert an NFA into its equivalent DFA. Let's get started. So if you want to convert an NFA into its equivalent DFA, it is required that you are given with an NFA so that you can convert it into its equivalent DFA. So here you can see given is a non-deterministic finite automata or an NFA. Here you can see we have given with an NFA and this is the 5-tuple representation of the given NFA. We know that the 5-tuple representation of an NFA contains 5 elements: Q, sigma, delta, Q0 and F. Q is the set of states of an NFA and you can see this set contains the elements Q0, Q1 and Q2, which means we have only 3 states in our NFA that are Q0, Q1 and Q2. This is sigma, which is our input alphabet, that is the set of input symbols. In case of the given NFA, we have only 2 input symbols, A and B. Delta is the transition function, Q0 is the initial state of the given NFA, and Q2 is the final state of our given NFA. So we are given with a non-deterministic finite automata. Now what do we want to do with this NFA? Our objective is to design an equivalent DFA for the given NFA. So we are given with an NFA and we need to design its equivalent DFA. What is the meaning of the word equivalent? Equivalent DFA means we need to create a DFA that will accept the language same as the language accepted by the given NFA. So to convert an NFA into DFA, we need to follow some sequence of steps. So let's see the procedure. Step number 1 is to construct the transition table of NFA. So we are given with the transition diagram of NFA and we need to convert this transition diagram into the transition table of NFA, which is a very simple task. Now let's see the step number 2. Convert the NFA transition table into the DFA transition table. So at the end of step number 1, we will get the transition table of NFA. In step number 2, we need to convert the transition table of NFA into the transition table of DFA. The step number 2 is the most important and the core part of this conversion. Step number 2 will further contain more sub-steps, which we will understand later. Step number 3 is to design the transition diagram of DFA. At the end of step number 2, we will get the DFA transition table. And from that transition table, we are required to design the transition diagram of DFA. So these were the 3 steps that we will follow while converting an NFA into its equivalent DFA. Let's start with the step number 1. Construct the transition table of NFA. So in this step, we are given with the transition diagram already and we need to convert that transition diagram of NFA into its transition table. So this is the transition diagram that is given to us and we need to convert this transition diagram into a transition table. Let's quickly see the transition table for this diagram. Here you can see we have 3 states in the diagram, Q0, Q1 and Q2, and we have only 2 input symbols. A and B. And in these cells, we have filled the next states. So Q0 on getting input symbol A. Let's see. Q0 on getting input symbol A, the next state is Q1 and also the next state is Q0. That is why we have written Q0, Q1 in a comma separated notation, because in NFA, we can have more than one next states possible. Q0 on getting input symbol B will reach the state Q2. So Q0 on getting input symbol B will reach the state Q2. Q1 on getting A will reach the state Q0. Q1 on getting A will reach the state Q0. Q1 on getting B will reach the state Q1. Q1 on getting B will reach the state Q1 itself. Now let's talk about the last state, which is the final state of the NFA, Q2. You can see Q2 doesn't have a transition for input symbol A. That is why we have written phi. Phi means no transition. You can also leave this cell empty if you want. Now, Q2 for input symbol B, the next states are Q0 and Q1. How? Q2 for input symbol B, we have the next states Q0 as well as Q1. That is why the next states of Q2 for input symbol B are Q0 and Q1. So this is the NFA transition table for the given transition diagram of NFA. In this way, we have completed our step number 1. Now let's proceed towards the most important step, that is step number 2. Convert the NFA transition table into the DFA transition table. I have told you that step number 2 is the most important and the core step of this conversion. And this is not going to be a very straightforward step. So you need to concentrate very well to understand this step. So we have got the transition table of NFA in step number 1. And now according to step number 2, we need to convert this NFA transition table into the transition table of DFA. How do we convert? So the header row of NFA table will be exactly same as the header row of DFA table. So while creating the DFA table, we will have the same header row, Q sigma AB, because A and B are the same input symbols in case of DFA also. Now we will fill all the other entries of this DFA table. So the first row of the DFA table will be same as the first row of NFA table, but with few necessary changes. In case of NFA table, you can see here we have the state Q0. On getting input symbol A, we are getting two next states, Q0 and Q1, which is allowed in case of NFA, but it is not allowed in case of DFA. In DFA, I told you, for every current state, there is only one next state possible for a given input symbol. So we have to combine these two states to form a single state. We have to remove this comma from between Q0 and Q1, and that will form a single state called as Q0 Q1. So let's see the first row of the DFA. Q0 is same. This Q0 Q1 is combined into a single state called as Q0 Q1, and this Q2 is also same. Also, you have noticed that we have put the square brackets instead of this curly braces. Why? Because in case of DFA, we are representing the single state. To represent the single state, we have put the square brackets. This is just a notation. Now let's talk about the next states of the DFA. We have got two new next states in this DFA that are Q0, Q1 and Q2. So we have to create the entries for these two states also. So here is the state Q0, Q1 and here we have the state Q2. Now we need to complete the transitions or the next states for these two new states. So if the current state is Q0, Q1 and the input symbol is A, what will be the next state? We can fill these next states by referring to the transition table of NFA. If the current state is Q0, Q1 and the input symbol is A, let's see. If the current state is Q0, Q1 and the input symbol is A, the next states are Q0, Q1 and Q0. So we have to take the union of these two states and we will get Q0 and Q1, which we will combine. So the next state will be Q0, Q1. And what about this cell? Q0, Q1, on getting the input symbol B, let's check. Q0, Q1, on getting the input symbol B, the next states are Q2 and Q1. Again, we have to take the union of these two states and we will get Q1, Q2 as our resulting next state of the DFA, which is of course a single state. Now let's talk about the state Q2. Now before completing the transitions for the state Q2, we are required to check whether we have got any new states while completing the previous transitions. So Q0, Q1 is already present in our DFA, so it is not a new state. But Q1, Q2 is not present in our DFA. That is why Q1, Q2 is a new state for our DFA. And that is why we have to create an entry for the state Q1, Q2. Now we can fill the transitions for the state Q2. Q2, on getting the input symbol A, what will be the next state? Let's check. Q2, on getting the input symbol A, there is phi. In case of NFA, phi means no transition, or you can say phi means no state. But in case of DFA, we cannot write phi. We have to replace phi with a special type of state which is called as dead state, which is represented using this. In case of NFA, this phi was nothing. But in case of DFA, this phi is a special state, as I have told you. It is called as the dead state, which is a separate valid single state of the DFA. Now, for the state Q2 and input symbol B, what will be the next state? For the state Q2 and input symbol B, we have two next states in case of NFA, Q0 and Q1. But in DFA, we have to combine these two states to form the single state, that is Q0, Q1. Now let's check whether we have got any new states or not. Phi is not present in our DFA. So phi is going to be a new state of our DFA. So we have to create an entry for the state phi, which is our dead state. And Q0, Q1 is already present in our DFA. So it is not a new state. Now let's talk about the state Q1, Q2. Q1, Q2, on input symbol A, what will be the next state? Q1, Q2, on getting input symbol A, the next states are Q0 and phi. Now phi is nothing, so the next state is only Q0. So here we will write Q0. Now for the state Q1, Q2 and input symbol B, what will be the next state? For the state Q1, Q2 and input symbol B, the next states are Q1, Q0 and Q1. On taking the union, we will get Q0, Q1 as a single state of the DFA. Now let's talk about our last state phi. Because in the previous transitions, you can see there is no new next state. Q0 is also present in our DFA and Q0, Q1 is also present in our DFA. So we need not to create more entries in our table. Phi, on input symbol A, the next state will also be phi, and phi on input symbol B, the next state is also going to be phi. But why? I have told you multiple times that when we reach the dead state, on getting any input symbol, we will still remain at the same dead state. That is why I have written phi and phi over here. Now let's check whether we have got any new next states. Phi and phi are the dead states already present in our DFA. That means we have not got any new states. So we cannot create further entries in this DFA table. And that is how we have reached the termination point of construction of the DFA transition table. In this way, we have converted the NFA transition table into the transition table of DFA. Now let's discuss few important points regarding this DFA transition table. Each DFA state represents a subset or combination of NFA states. Hence, this method is called as subset construction algorithm. So every state in this DFA represents a subset or combination of NFA states. What were the NFA states? In the beginning, I have told you there were three states in the NFA, Q0, Q1 and Q2. And if I create the set of these three states, Q0, Q1 and Q2, what will be the subsets of this set? Only Q0, only Q1, only Q2, Q0, Q1, Q1, Q2, Q0, Q2, Q0, Q1, Q2, and phi. So there will be total of 8 subsets possible for the states of NFA. And according to this point, every state of this DFA is a subset or combination of the NFA states. And that's true. This is the reason why this method is called as subset construction algorithm or subset construction method. Now, can you answer one simple question? Is this DFA transition table complete? No, it is still not complete. One small but important thing is left. We have still not identified the initial and final state of this DFA. So what will be the initial state and the final states of this DFA? Let's see. The initial state of the DFA is the initial state of the NFA. And we know the initial state of NFA was Q0. So the initial state of DFA is also Q0. What about the final state? Any DFA state containing a final state of NFA becomes a final state. What was the final state of NFA? Q2 was the final state of NFA. And according to this point, any DFA state containing the final state of NFA will become the final state of the DFA. So out of these states of the DFA, which state is containing Q2? That was the final state of NFA. These two states contains Q2. That is why these two states will become the final state of this DFA. In this way, we have identified initial state and the final state of this DFA. Now this DFA transition table is 100% complete. Now there is one last point left to discuss, which is very important for the competitive exams like GATE. Let's see. If an NFA has n states, then the equivalent DFA can have at most 2 to the power n states. So if I have total n states in DFA, then the number of states in the equivalent DFA can be maximum of 2 to the power n. So if I have 2 states in NFA, the maximum states in DFA can be 2 to the power 2, which is 4. If I have 3 states in NFA, the maximum states in DFA can be 2 to the power 3, which is 8. So this was a very important point that you need to keep in your mind. These were the 4 important points that we have discussed regarding the transition table of this DFA. In this way, we have completed our step number 2. Now let's proceed towards the step number 3. Step number 3 is design the transition diagram of DFA. So we have got the transition table of DFA, and now we need to construct the transition diagram of this DFA, which is a very simple task. Let's start constructing. So first of all, we'll have our initial state, which is Q0. On getting the input symbol A, we are reaching the state Q0, Q1, which you can see. Q0, Q1 is now a single state of DFA, which were 2 separate states in case of NFA. Q0 on getting input symbol B, we will reach the state Q2. Q0, Q1 on getting input symbol A, we will reach the state Q0, Q1. Here you can see we have created the self loop of A because we are getting the same next state. Q0, Q1 on getting input symbol B, the next state is Q1, Q2. So we are getting the state Q1, Q2. Now, for the state Q2, on getting input symbol A, we are getting the next state as the dead state. So, we are getting the next state as the dead state. For the state Q2 on input symbol B, we are getting the state Q0, Q1. So, for the state Q2 on input symbol B, we are getting the state Q0, Q1. For the state Q1, Q2 on input symbol A, we are getting Q0. For the state Q1, Q2 on input symbol A, we are getting the state Q0. For the state Q1, Q2 on getting the input symbol B, the next state is Q0, Q1. So for the state Q1, Q2 on getting the input symbol B, the next state is Q0, Q1. And for the dead state phi, on getting any input symbol, either A or B, we will still remain at the dead state. So we will simply create a self loop of the symbols A, B over the dead state. This was the transition diagram of the DFA that we have constructed from the transition table of DFA. In this diagram, you can see the names of the states are quite lengthy, like Q0, Q1, Q1, Q2. In other problems, the names can be even more lengthier, like Q0, Q1, Q2, Q3. So it is not always convenient to write such big names. So we can replace the names of the states using the uppercase letters like A, B, C, D, E, and so on. So in this way, we have completed our step number 3. I hope you now understand how to convert an NFA into its equivalent DFA. Now, before ending this lecture, I have one simple homework problem for you. If the number of states in an NFA is 5, what can be the maximum number of states in its equivalent DFA? So find the answer for this question, and once you find the answer, do not forget to post it in the comment section. This is how we have completed our topic, the conversion of NFA into its equivalent DFA. From the next lecture onwards, we will solve few problems on NFA to DFA conversion. This was all from my side for this lecture. Thank you, and I'll see you in the next lecture.